Hi, everyone. Continuing on the second day in my office with lecture number 3. Let me share my screen. So in the previous lecture, we talked about how to do some direct measurements of capture reactions. Again, there's a lot that we skip, but that's kind of the basic idea of how to measure these reactions in regular kinematics and in inverse kinematics. So today we'll kind of dive into nuclear structure. And one way to do that is through indirect measurements. Those include a lot of nuclear structure. And then we'll go into various techniques in nuclear structure. So indirect measurements. There are many reactions that are either completely impossible to measure in the ways that I showed in the previous lecture, or maybe they're just hard, or maybe we can use them down to a certain energy, but because the cross sections get smaller and smaller, then it becomes hard to get any reasonable result with those low cross sections. And so for all of these cases, we have to figure out a different way to constrain these reactions. And even though we cannot measure them directly, it's still, in most cases, we can provide enough constraints to learn something about the reaction and still have a meaningful input into the astrophysical model. I'm showing here some examples of indirect techniques. You can see already it's a long list, and there's a lot more than I probably missed. So we can use, for example, transfer reactions, DN or DP reactions. I showed this on the first day, where we kind of use this DN or the DP reaction to sneak into the nucleus a proton or a neutron, and this way just study what's going on with the nucleus when it captures one of those protons or neutrons, even if they are as a part of the deuteron. We can use beta decay to feed various levels of interest, and then we can get branchings. For example, just see the competition between gamma ray and alpha emission, or gamma ray and proton emission, or just the different gamma rays emitted. So you can get information about that. You can also get information about the spin this way. And also you can use various reactions to get information about spins. The Trojan horse method is a method that has been extensively used, especially for lighter masses and going to low energy reaction rates. And I'll encourage you to look it up. I'm not an expert at all, and so I'm not going to go into this in this talk, this lecture. But again, it's just a way to kind of sneak into the nucleus the particle that you're interested in. The Surrogate method, I'll talk a little bit more about that in terms of neutron-capture reactions, and also the Oslo method. This is my expertise. My research has been focused on this method for a while now, so I'll talk more about that. We can use various reactions again to extract the nuclear level density or the gamma ray strength. I showed this in the first lecture, that these are quantities that are important in terms of calculating the neutron capture rates. And so if you have a way of measuring the nuclear level density or the gamma ray strength, then this provides a nice constraint to the calculation of the neutron capture. You can use Coulomb dissociation for the extracting again the gamma ray strength, especially this is at higher energies, and it goes on and on. There are many other things that you can do. So for this lecture, I'm going to focus on neutron capture reactions. Again, this is my expertise, and I can show at least some details about it. So what's the problem with neutron captures? We saw yesterday, or in the second lecture, that we can use regular kinematics to measure a reaction. So we could use, let's say, a neutron beam hitting a heavy target. But if the heavy target, the heavy nucleus, is something that is radioactive, for example, short-lived, then this doesn't work very well. You could get the radioactive beam and flip it and do inverse kinematics. So now you have the heavy beam coming in, but it would have to hit a neutron target. And we don't have neutron targets available, at least definitely not in the densities that we would need to do these reactions. And so we're kind of stuck. There are ideas and ways, creative ways that we're thinking about to do these kind of experiments, where you would have maybe a neutron beam hitting a radioactive beam. So far, we haven't been able to get enough intensity for this, but it's still, for the future, or have some other way of creating a neutron target that is not exactly the traditional way. So there are thoughts, but for now, right now, all we can do is just use these indirect techniques. So that's what I'll talk about. One of these indirect techniques is what is called the surrogate technique. So for this one, you would use typically a deuteron, but it could be other things. But typically you would use a deuteron to sneak into the nucleus that neutron that we want to sneak in. So the desired reaction is a neutron going into nucleus A and creating A+1 excited. Instead of doing that, then you would do a deuteron, and then the proton flies off, and again, you have the neutron sneaking in here and creating the same nucleus. Then there's a process of getting this, the information that you need. So you have to take into account the reaction theory involving the deuteron and the proton on this part, on this side. And then of course, what happens to the excited nucleus. So there's a group, you can find information here, and there's actually, I forgot to put in the most recent publications. There are 2 papers in Physical Review Letters where they show how this works very nicely. On the other hand, you can do what I mentioned before. I showed this slide earlier, where what we want to do is get the neutron-capture reaction, and the properties that matter in terms of calculating this are the level density, the gamma ray strength, and the optical model potential. And so if we can measure these, especially the first 2, we would be constraining significantly the neutron-capture reaction. So again, this is the same slide I showed before. So what we've done, my thingy, there we go. So there is a method that does exactly that, extracts the level density and the gamma ray strength for various nuclei, that is called the Oslo method. Say here the traditional Oslo method, and I'll describe this, and then I'll show you a variation that we came up with the last 7 years or so. So the idea here that you use a reaction to populate the nucleus you're interested in, and you need to know the excitation energy you're populating. This is on this axis here. And you also need to know the gamma ray energy that's coming out from each of these excitation energies. If you have this information, you can kind of unfold with the response of your detector and so on. And you can do, it's a kind of iterative subtraction process to try and figure out what is the first gamma ray that's coming out of each excitation energy. And it's a statistical method, so it's not that you know each gamma ray, which one is the first gamma ray, but you just get a distribution. You get a probability to get from this point to emit a gamma ray and go to this point, or again, from the same entry state to emit a gamma ray and go to a lower point, and so on. And this probability, it depends on 2 things. It depends on the level density at the endpoint, and it also depends on the gamma ray strength, which is just the probability to emit a specific gamma ray as a function of energy. So this looks like that. This is not the gamma ray strength, this is the transmission coefficient. Again, I mentioned those in the first slide, but it's a very easy transition to go from one to the other. So the group in Oslo has been using this for a very long time, and this is just the proof of principle where the lines are the calculation that comes after constraining the level density and the gamma strength with this Oslo method, and the data points are the ones that are measured directly for one of the reactions. So this technique works very nicely. I showed an example, so I'm going to skip this slide. So the variation we came up with is called the beta Oslo method. So instead of using a reaction to populate the nucleus that you're interested in, we are using beta decay. The advantage of beta decay is that every single nucleus that you implant into your setup will decay. So if you have a beam intensity of 1 particle per second, then after an hour, you already have 3,600. And very quickly within half a day or a full day, you have accumulated a lot of statistics, which you would need a week or 5 weeks if you were using any kind of nuclear reaction to get the similar amount of statistics. So this is the advantage of beta decay. On the other hand, beta decay might be very different than neutron capture. And so these are considerations we have to take into account when we're trying to constrain neutron captures coming from beta decay. The other problem is that like in the Oslo method, where you need to know the excitation energy, you cannot really get this from beta decay because that beta particle doesn't give you all the information. There's a neutrino flying out that carries some part of the energy. And so you never know exactly which level you're feeding just by measuring the beta particle. So the way around this is to just measure all of the gamma rays that are coming out. I showed the summing technique in the previous lecture. So this is a kind of a summing technique. You measure all of the energy that is coming out, and then you know the excitation energy. And then if your detector is segmented, like this one here, this is my group's detector, Sun, then you can also get the individual gamma rays. So you get all the information you need for applying the Oslo method, and this is what we've been doing for a while now. Here's a sample matrix with excitation energy versus gamma ray energy. We applied these in the region of the weak R process, which I didn't say much about, but it's kind of in the intermediate mass region. It's a R process conditions that could just produce these intermediate mass nuclei. Here's just an example of how this looks like coming from beta decay. So the uncertainty coming before the measurement, just from the models, the variation in the models is quite large. These nuclei are quite a few steps from stability where the models are not very well constrained. And so after the beta Oslo constraint, then you end up with this darker band, which is much, much better than what you had before. It's still not in the accuracy that you would get with a direct measurement, but since we cannot do a direct measurement, this is actually good enough. To get an idea of where you can apply the various techniques, I'll say that in this is a chart of nuclei, and this shows you, the color code shows you how much the various theoretical predictions vary for these different nuclei for neutron capture reactions. So if we're close to stability, then all the predictions are within a factor of 5 or so. That's the green color. But very quickly, as soon as you go 2-3 steps from stability, we're talking about variations that could be up to a factor of 100 or even more in some cases. And so this is why we need to have experimental data, experimental constraints, even if we cannot measure these reactions directly. So with the techniques I've been talking about, if you would have a stable beam, like a neutron beam, hitting a heavy target and so on, you could do the stable isotopes. If you would use a reaction-based technique like the Surrogate method or traditional Oslo method with a radioactive beam, then you could reach maybe these first few nuclei from stability. And then with the beta decay, you can shoot quite a bit further out. So this is, again, a complementary approach of the various techniques, because with the beta decay, we actually cannot go much closer to stability. The beta decay Q value, the available energy, is just too small and we cannot do it. And with the radioactive beam, with the reactions, we cannot go far away. And so these are completely complementary. Okay, switching gears a little bit and going back to nuclear structure. And you can say, well, reactions is what we care about. Why do we even care about nuclear structure? And this is this one picture that I just love to show. This picture, it shows the direct connection between nuclear structure and nuclear astrophysics. And I mentioned this already on the first day. So this is a chart of nuclei. In the blue line here, we represent the S process. In the pink line, we represent the R process. And up here, you have the abundance distribution. Blue is, again, S process, and red is the R process. So what is happening is, if I get the R process, you kind of have the flow, the competition between neutron captures and beta decays, and it all stalls right around the neutron magic number. And because of that, then there's a peak that is formed in the abundance distribution. That is this peak. There's another peak that comes from up here. Oops. Now, the R and the S process, again, the S process will meet the magic number, but it will meet it a little bit heavier in mass. And so the S process peak coming from the exact same magic number is a little bit higher. So this just shows you, you get this abundance distribution that comes from a star. It can be a distant star, it can be within the solar system, but you just get these abundances of the elements. And the reason that there's this structure in the abundances is just the pure nuclear physics properties. This property that there's a magic number, the nuclei like to stick to that number and not change and not become its neighbors. So figuring out the magic numbers is important. That's the bottom line. So mass measurement is a very good way of getting the magic numbers. It's not the only way, but mass measurements are important for many things. And one thing is to get the magic numbers. And so, for example, here, we can plot the two neutron separation energy as a function of neutron number. And what we see is that right around n equals 20 and n equals 22, you get these jumps like this. This is the most impressive one. You get these jumps in the two neutron separation energy. And this is an indication of these magic numbers, the same here. Now, this is a very cool picture because you can see that as you go to heavier and heavier elements, then you can see that you don't have that big jump anymore. See here, you can still see it, but this one maybe not so much, and definitely not so much here. So there is an evolution in these magic numbers that we cannot predict very easily. We really have to go and measure and see how these magic numbers behave far from stability. And the art process is definitely far from stability, so we definitely need to keep an eye on that. There is an impact of the masses on all the astrophysical observables. So for example, here's a calculation of the abundances for different mass models with the current uncertainties, which is this huge band over here, versus if we could improve our uncertainties a lot more, what would happen? And so you can see the impact or the reason to go and measure masses because we need them to constrain our models. And this is another example where the masses, they fall into the proton separation energy. And so you can see for various values of these proton separation energies, you get a completely different distribution of light. This is the luminosity in X-ray bursts. So you can see how masses are important. There are many other examples, of course. Let's see. So masses are important. We need to measure them. I'll show some examples here of how you will go about to measure masses. This is a nice picture I got from Zach Meisel's PhD thesis that you can find online, where you see what is the typical precision of a mass measurement versus how long it takes to do the measurement. So for example, time of flight measurements are the shortest, they're very fast to do, but their precision is not great. It's maybe 100 keV or so. There are, other ways that you can do these measurements, this storage ring, MR-TOF. We will talk about this a little bit later. It's some kind of a time of flight. Penning traps are the best. Penning traps, this is together with another storage ring technique. They do have the longest time to measure, but they give you a very good precision. So depending on what you need, if you need just a whole bunch of nuclei measured quickly, then you do the time of flight. If you want the one nucleus, but you want to measure very accurately what's going on with the mass of this nucleus, then you better choose a different technique. And so depending on what you want to do, you can choose. The penning trap, if you're not familiar with it, is basically a trap that uses electric and magnetic fields to create some kind of a cyclotron motion inside it for the ions that go in. It's a triple motion. So you can see here, it's one motion like this, another one that goes up and down, and then another one, which is the little circles. And so with this motion trapped inside the trap, then in principle, if you calibrate your trap, then you know everything except for the mass of the nucleus that is there, and you can use, you can extract this. This is kind of what the traditional measurements look like. You have very accurate measurements. For example, you can also have within the same nucleus, you can measure the ground state and an isomeric state, which is also very nice. So yeah, this is a very good accurate technique, and penning traps exist in most of the large nuclear physics facilities around the world. Is just an example of various penning trap measurements that was published it's close to a decade ago. So there are new measurements now, but I like this picture. It just shows a comprehensive measurement presentation, and it shows how we're reaching now the art process path. We're not completely there yet, but we are reaching the art process path. And so it's exciting to get even more closer to the art process path, and we'll be able to get there with the next generation facilities that can give us the right beams. Time of flight is basically what the words say. You measure the time it takes for ions to go from point A to point B. And if you know the time it took to get there and you know their velocity, you can figure out their mass. So you have to do a lot of work to calibrate your setup. So you could be measuring, I don't know, 10, 20 different beams and use those as calibrations. And then you have the two new beams, like the red ones here, to provide the new masses. But you are limited to how long of a time of flight you could have in your facility. This is the NSCL. And so we could go from the beginning of the facility all the way to the end of the facility. It's about 90 meters. And that was the longest that we could do. In order to improve, to increase the flight path, you can just have these, have reflections. And this is what's going on with MR-TOF. So it's a multi-reflection time of flight. And you can do it in many different ways with just one setup. The beam goes back and forth. You can just do one reflection. You can do kind of a circular reflection. There's many different ways that you can do that. But the point is that you're increasing the flight path. And so you're improving your measurement accuracy. Storage rings have been used a lot in mass measurements, and you can, depending on the accuracy you want, you can use two different ways. You can use what's called the Schottky mass measurement or the asynchronous mass measurement. And again, one way is giving you a much better accuracy than another way. I'm not going to go into details here. I'm just mentioning it so that we kind of have an idea that this exists, and we can discuss it more when we meet. Okay, moving on to beta decays. Beta decays, we saw already that measuring half-lives, measuring beta delayed neutron emission probabilities, those are two very important quantities. There's a third quantity we haven't talked about, which is called the beta decay intensity. And this is sometimes it's useful directly to know for the astrophysical environment, but quite often it's just used as a model comparison, a model to inform the model, a model constraint. I got it. So the beta decay intensity, what it is when you start with a nucleus and it will, you have the beta decay feeding various excitation energies, then the beta decay intensity just tells you what is the probability to feed this point here versus this point and so on. This is an important quantity because then you can compare it to the model and you can provide a very sensitive comparison, unlike the half-life and the beta n value, where it's just one number and either you get it right or you don't get it right. You don't get enough detail. So in terms of the half-lives, of course, half-lives are important, and we've seen that many, many times, but just showing a sensitivity study that shows that with the uncertainties in half-lives that we have right now, or that was in 2016, then you get the abundance predictions you get vary by quite a lot. And so we do need to have all of those half-lives measured. Every time there's a new facility that comes online, then we have access to a whole new set of nuclei. And this is what happened most recently at RIKEN. So this was the first paper that came out of when the RIKEN upgrade was completed back in 2014-15 was the paper where they measured a whole bunch of new half-lives. And you can see here what was known and what's what was known before is what's left on this line. And so there was a lot of new half-lives measured. And here you can see the art process calculations without the new half-lives and with. And so you can see these big fluctuations in the abundance distribution that then got resolved. Switching now to high resolution spectroscopy. This goes back to nuclear structure and understanding the evolution of the magic numbers and the evolution of the various shells. And so it's important to do this kind of nuclear structure measurements. There are various setups around the world. I'm showing here two examples. This is the SEGA detector at MSU, the Griffin detector at Triumph. There's, of course, the new high resolution arrays that are available around the world, Agata in Europe and Greta or Gretina in the US. So all of these are devices that provide a lot of high resolution information for these kind of measurements. So the idea here is that you're trying to figure out the shell model, the level structure, and you do that by measuring, maybe you measure the ground state or the first excited state or the first low-lying states in various nuclei. You can do this very nicely with high-resolution spectroscopy, unlike other kinds of spectroscopy, because then you can see the peaks very nicely. You can, the peak to background ratio is very strong. Switching to beta decay intensity, this is the opposite of high resolution spectroscopy. You need a very efficient detector that typically doesn't have a very good resolution. But if you can do this kind of measurement with a very large detector, you know exactly the energy that you're feeding. And then you can make plots like this, where you plot the strength or the intensity. This here is what is called the Gamow-Teller strength. But it's connected to the beta decay intensity. So you plot that as a function of excitation energy. And you can see here the data points are these black points, and you can compare to various models that predict the shape of the nucleus. So here the prolate shape was perfect, spot on compared to the oblate shape, which was not even close. This is kind of a textbook case of a measurement like this. Typically, your data points look something in between, because there's typically contributions from both, or the shape is not so clean, but here this was a beautiful result. So the idea, again, is that you have beta decay feeding the various excited states. And the problem is that you find it in the literature. The problem is called the Pandemonium effect. So from John Milton's poem, Paradise Lost. And the Pandemonium is basically, if you use small size detectors like what you would need for spectroscopy, then you can't figure out all the tiny little gamma rays that are coming up here, or you know, the very large energy gamma rays you might miss. So you might miss some of the intensity and not be able to assign it to the right excitation energy. While if you have this large volume colorimeter detectors, then you can assign exactly the right excitation energy. So this is an example of what that Pandemonium looks like. For a nucleus that's it's very close to stability, where there's a lot of measurements that took place in the past. So this is gallium-76 decaying into germanium-76. We see that NNDC here just means what's available in the literature. We see that if you compare what the total absorption spectrum looks like, this colorimeter spectrum looks like, compared to what's known in the literature, those two, they're close. It's not a huge discrepancy, but they don't quite agree so well. There's an extra peak here that should be assigned, this intensity should be assigned somewhere higher energies, but it's close. But this is because we have enough data. If you go further away from stability, so here is zirconium 101 going into niobium 101, then you can see that there's a huge difference between what is known in the literature and what you would get with a total absorption spectrometer. So this motivates, it shows that it's very important to measure with these large size detectors. Even though we don't get all the detailed information on the spectroscopy, we still get the full picture on the beta decay intensity, which is important. I think I'll skip this for now. And now moving to PN values. So beta delayed neutron emission is very important for various reasons. One is that it defines the path going back to stability after the R process is done. So we need to know exactly what that path looks like. And the second is that when it happens, there's a neutron released after each of these beta PN beta delayed neutron emission. And so those neutrons will go back and induce more neutron capture reactions. So we need to have the right balance over there and know how many neutrons we have available. So this is a sensitivity study where the blue line shows what's going on with the abundances with beta delayed neutron emission, and the red one is without. So they just remove it completely. The truth is somewhere in between probably, but this is kind of an extreme to see what the behavior is. And we see that for a hot wind environment, this is not a huge difference, but for cold wind and neutron star merges, we do see a difference if we take the beta delayed neutron emission into account or not. So to measure those PN values, you can do two things. One is you can measure, you can integrate over the energy and just say beta delayed neutron emission is 5%, and that's it, just one number. or you can get information about the intensity as a function of excitation energy. And so if you want the integrated version, you need a detector like this. This is a helium-3 based with a moderator around it. This is NERO at MSU, but again, this kind of detectors exist all over the world. If you want to get detailed spectroscopy of what these neutrons look like, then you probably need a detector like this. This is Vandal from ORNL, or this is the detector they have at Triumph. So again, you get information about all the different energies of the neutrons. And finally, you can also measure better delayed neutron emission in a very cool way, in my opinion, where you don't even need to measure the neutron. So that's why I like this technique a lot, although I've never used it myself. But the idea here is that if you have a nucleus decaying right here in the center of, you have a trap, you have the nucleus decaying right here. There's a beta particle going off this way. And let's say there is a neutron emitted, it goes that way. It will not be detected, it just goes off. But the fact that the neutron is emitted, it kind of gives a little kick to the recoil nucleus. And so this recoiling nucleus will travel and will hit one of your detectors. If there was no gamma ray emitted here, then this nucleus would not have such a kick and it would just travel there slower. So you just measure a time of flight in the end. This is time, just counts for exactly this case here. And so if you do have the neutron, better delayed neutron emission, then your nucleus has an extra kick and it goes faster. And so you see the nuclei arriving at a shorter time. But if you don't have that neutron, it's just the beta decay, then everything is just quite a bit slower. And then you see the slower distribution. This is just from the gamma rays, and this is with the neutrons. So you can measure the probability for the neutron emission without even measuring the neutron, which is pretty cool. This is, as just an example of recent PN measurements that took place at RIKEN. Again, this is important to know that every time there's a new facility coming out, then you have all these new capabilities. And so there's a lot of new measurements coming out of these facilities. So this is what happened with RIKEN, again, with better delayed neutron emission as well as half-lives. So this kind of concludes all of my lectures. We covered a lot, and I know I went fast, but I'm looking forward to have discussions with you and cover more details or answer your questions. We did not cover everything. There's so much we didn't include here, and there's so much I just don't have the expertise to tell you about, or I just didn't have the time to tell you about all of that. So some examples of what we did not cover are isomers, charge exchange reactions, I very briefly mentioned at some point, PN reactions for the nu-P process, alpha N reactions for neutron star cross, equation of state experiments. There's a lot going on. Fission is a big thing that we didn't touch at all. So there's a lot that we skipped, but I hope the ones that we did cover, that they were clear, and I will look forward to talk about all of this with you soon.